Assalamu alaikum. This is lecture 8 of data security and encryption. In this lecture we are going to discuss about block and stream ciphers. The objective of this lecture is to illustrate the principles of modern symmetric ciphers. This will also contain a discussion of general principles of symmetric block ciphers, which are the principal type of symmetric ciphers. Let's briefly look at the lecture contents. In this lecture, we are going to discuss about the traditional block cipher structure, that how a block cipher is formatted and used in the data transmission. Then we are going to differentiate between the stream ciphers and block ciphers and their respective implementation in network security and information security systems. Then we will highlight the motivation of a commonly used cipher structure known as Feistel Cipher Structure. And finally, we will discuss the implementation of Feistel Cipher Structure. So at the end of this chapter, you should be able to understand the distinction between stream ciphers and the block ciphers, and you should be able to present an overview of the Feistel cipher and explain how decryption is the inverse of encryption. So the current analysis and the numbers shows that several important symmetric block encryption algorithms in current use are based on a structure referred as Feistel Block Cipher. For that reason, it is important to examine the design principles of Feistel Cipher, and we are going to discuss a comparison between stream ciphers and a block cipher. Then we will discuss the motivation of Feistel block cipher structure, and we will discuss its implication. So first of all, let us define what is the difference between a stream cipher and a block cipher. You should be a little bit familiar with the stream cipher, that it is used to encrypt a digital data stream one bit or one byte at a time. So examples were discussed in the last lecture, such as use of auto-keyed Vernier cipher and the use of Vernon cipher. If you recall the Vernier cipher, it was based on the Caesar cipher with a random key taken a mod with the 26 or any number of keys that are used from for example A to E or A to Z, and it was the key was added with the plain text, and it was taken mod against the 26, and the cipher was generated. Similarly, if you recall the second named Vernon cipher, you should understand that in that cipher we used an exclusive OR algorithm that was used to embed the plain text with a cryptographic stream of bit, and the result was a ciphertext. So stream cipher is also can be used in the ideal case. A one-time paired version of Vernon cipher would be used, in which the key stream is as long as the plain text bit stream. So we discussed in the last lecture that the stream can also be used as long as the key itself. So if the cryptographic key stream is random, then the cipher is unbreakable, as we discussed in the last lecture, that a one cipher with a uh, one-time pad can be an unbreakable cipher. So that means any other by any means other than requiring the key stream. Key stream must be provided to both the user in advance via some independent and secure channel. So this was also the precondition that the key must be transmitted to both the user, and this was also a challenge in implementation of one-time pad version of Vernon cipher because it is very difficult to actually uh, transfer the keys to the user where there is a huge amount of data is transferred. So this also introduces a unsurmountable logistical problem. That means the problem for distribution of the keys if the intended traffic is very large. For practical reasons, the bit stream generator must be implemented as an algorithm procedure so that the cryptographic bit stream can be produced by the both users. So it can be a precondition of a stream cipher that your algorithm should generate the bit stream as a independent function. So it must be computationally impractical to predict the future portions of the bit stream based on the previous portions of the bit stream. The two users need to share the generating key and each can produce the key stream. On the other hand, a block cipher is a block of plain text that is treated as a whole rather than bits, and it is used to produce a cipher text block of equal length. For example, if you take the block of 16 bits from the plain text, you generate a ciphertext of 16-bit for that plain text. So typically, size of the block can be 64 or 128 bits. So these are the normal range of blocks. 64 has been in use. 64 bits has been in use for a long period of time. However, recently 128 bits of the blocks are in use. So as with the stream cipher, the two users share the symmetric encryption key. Similarly, block cipher will also require the distribution of symmetric encryption key. So the majority of network based symmetric cryptographic application make use of block ciphers the rather than the stream cipher. So in practice, a lot of effort has gone into analyzing the block cipher. In general, the block ciphers seem more applicable to the broader range of application than the stream ciphers. Therefore, most of the application prefer the use the block cipher. And our focus of discussion will also primarily on the block ciphers. So this diagram actually shows the representation of a stream cipher using the algorithmic uh, bit stream generator and a block cipher. So you can see that in a stream cipher, the bit stream generator is a key controlled algorithm and it must produce a bit stream that is cryptographically strong. So key can be generated by a bit stream generation algorithm and which is embedded with a plain text to produce a ciphertext. On the other hand, the decryption algorithm must also use the same function called the bit stream generation algorithm and it embeds the key with the ciphertext to produce again the original plain text. On the other hand, if you are using a block cipher, you actually input the key to the encryption algorithm along with the plain text. But in this case, the plain text is not a series of bits, it is a number of bits, that means a block of bits are taken, such as 64 bits or 128 bits of the plain text is taken as an input to an encryption algorithm and along with the key to actually transform it to a cipher text. Similarly, in the decryption side, it takes the ciphertext as an input and the key along with that, and it will produce the same amount of plain text as it was taken in the input number of B bits. So a block cipher operating on a plain text of block of n bits to produce a ciphertext block of n bits. There are 2 raised to power n possible different plain text blocks. And for the encryption to be reversible, it means that your encryption or encrypted message must be able to be decrypted for at the end of recipient. So each of your bits must produce a unique ciphertext block, such as transformation is called reversible or non-singular. For example, if you use 2 bits of any 2 bits to transform your text from plain text to your ciphertext. So for example, if you have two inputs 1 0 and 1 1 and you transform these inputs to 0 0 or let's say 0 1, so these are unique ciphertext blocks for each input. On the other hand, and these are reversible, I mean if you decrypt this message, you have the encryption key that tells you that wherever you encounter 2 zeros, you can replace it with 1 0, and if you encounter 0 1, you can replace it with 1 1. On the other hand, if your encryption algorithm produces a different output in the same case, for example, we have the same input 1 0 and 1 1, and our algorithm produces the input 0 1 and 0 1. And so at the end of at the end of recipient, when you apply the decryption algorithm, 0 1 will be translated to 1 0 in many cases or in all cases. Similarly, 0 1 can also be transferred to 1 1. So this will create an ambiguity of your in decryption algorithm, and you may lost most of the data using this uh, confusion. So this kind of algorithms are usually marked as irreversible algorithms. So this diagram actually illustrates the logic of a journal substitution cipher for n bit algorithm. So for this case, we are using n is equal to 4. That means we will have 4 bits of input, and we will want to have the 4 bits of output. So typically a 4-bit input produces one of 16 possible input states. For example, if you use 4 bits for any number system representation, you have 16 possible combinations. So which is mapped by the substitution cipher into a unique one of 16 possible states. So if you want your algorithm to be uniquely identified and reversible at the decryption end, you want these 16 states to be actually unique. There should be no duplication of the uh, any of the 16 states. So each of the states which is represented by the 4 cipher text bits. So this is the most general form of block cipher, and it can be used to define any reversible mapping between the plain text and the ciphertext. So Feistel refers to this is an ideal block cipher because it allows for the maximum number of possible encryption mappings for the plain text block. However, there is a practical problem with the ideal block cipher. For example, if a block is very small, such as in this case, if we have only 4 bits using for the system, so this is actually equivalent to the classical substitution ciphers that we have used in the last lecture. So such systems that we have seen already are very much vulnerable to statistical analysis of the plain text. So this means such kind of systems If you have fixed output for each of the 16 inputs, your attacker can identify the patterns and can get the statistical information to actually decode the message. So this weakness is a problematic in substitution cipher, especially when you have a small block size. So if on the other hand, if n is sufficiently large and it is also reversible between plain text and ciphertext, then the statistical characteristics of source plain text are masked with such an extent that cryptanalysis is very difficult. So if you have large number of input bits, for example 64 or 128, it is very much difficult than the 4 bits to actually analyze the patterns in the ciphertext. So if we go to the diagram, we get a 4 bit input from here. You can see a bit 1, bit 2, bit 3 and bit 4. So these uh, are mapped with a 4 to 16 decoder. That means there are 16 possible states for 4 bits, such as representing on and off, and there is a different connection between each of the bits to actually uh, specify these bits to another form or a cipher. So these bits are provided to encoder to provide a 4-bit output cipher. So this table represents two examples of reversible encryption and decryption substitution ciphers. So mappings are defined by the entries in the second column. So these specify the plain text such as input, and these the next columns specify the outputs or the cipher text. So this determines the specific mapping from all the possible inputs. In this case, using a straightforward method of defining the key that is required, the required length should be equal to 4 bits, and there are 16 possible rows. So in total, we will have 64 bits of data or keys. In general, for a n-bit ideal block cipher, the length of key defined by the fashion is n steric 2 raised to power n. For, for this case, we have 2 raised to power 4 bits, and we have n is equal to 4. So we get 4 cross 16, that is equal to 64 bits. Similarly, if we use the 64-bit block, which is a desirable length, to remove the statistical attacks, the required key length will be equal to n cross 2 raised to power n keys. So this will be a very huge amount of keys used in form of bits. So our encryption or decryption algorithm will be very much secure from the attacks. So one algorithm proposed by the Feistel is uh, specifies that we can approximate the ideal block cipher by utilization of concept of product cipher, which is an execution of two or more simple ciphers in sequence, such as you can use a Caesar cipher and you can take the product with a Vernier or Verman cipher. So the product should be such a way that the final result is cryptographically stronger than the individual ciphers. It means if you combine two ciphers, your end cipher must be stronger than the individual ciphers or the combination of both ciphers. This approach is to develop the cipher with a length of key. For example, a key can be any number of bits. We can represent the key by k, and the block of length is represented usually by n bits. So it should allow 2 raised to power k bits uh, possible transformations rather than 2 raised to power n transformation available for the ideal block cipher. So Feistel proposed the use of cipher that alternates substitutions and permutations. So if we define each of these terms briefly, a substitution means each plain text element or group of element is uniquely replaced by corresponding ciphertext element or group of elements. That means you substitute the value with some other values. Permutation states that no elements are added or deleted or replaced in a sequence rather than the order of in which the elements appear in the sequence is changed. That means no new element is added or substituted, only the original plain text is shuffled so that the sequence is changed. So Feistel Cipher is a practical application of the proposal by Claude Shannon to develop the product cipher that alternates the confusion and the diffusion functions. So before we look at the concepts of confusion and diffusion, uh, it is very important to state a remarkable fact here. The Feistel cipher structure, which dates back to 1945, is a structure used by number of symmetric uh, block ciphers. In particular, Feistel cipher structure is used by data encryption standards and triple data encryption algorithms. So, which is one of the two main encryption algorithms using uh, uh, Feistel structure along with advanced encryption standard algorithms, and it is approved by the National Institute of Standard and Technology. So the terms introduced by Claude Shannon to capture the two basic building blocks for any cryptographic system. So Shannon's only concern was to minimize the cryptanalysis based on the statistical analysis. So so they have done using the diffusion and confusion. So, for example, an attacker has some knowledge about the statistical information about the plain text. It can be in a human readable message in some language. It can be a frequency distribution of various letters or in some other form of words or phrases that are likely to appear in the messages. So if these statistics are in a way that are reflected in the ciphertext, and the attacker may be able to deduce the encryption key or some part of encryption key or at least a set of encryption key which has the exact key, so the text can be compromised. So the two methods suggested by the Shannons are diffusion and confusion. So this will actually enhance the credibility of the cipher, and it will minimize the attacks options. So diffusion states that the statistical structure of the plain text is dissipated into long range statistics of the ciphertext. So that means you have to diffuse the obvious patterns so that the patterns cannot be easily discovered. So this is achieved by having each plain text digit affect the value of many ciphertext digits. So an example of diffusion is to encrypt a message. Message can be represented by M, and it can have number of sub messages or sub bonds. So a message can be encrypted. Message M can be encrypted with an averaging operation, such as done in the Wiener cipher or Verman cipher. For example, if we take the Wiener cipher, we take the message bits and we take the mod of each bit with the 26 and we diffuse the values to a wide range of set of values so that the statistical analysis cannot actually reveal the actual structure of data. So it can be also achieved by adding some random bits between the data so that the regular pattern may be disturbed and the attacker will not be able to identify the patterns. Or in other ways, such as in binary block ciphers, diffusion can be achieved by repeatedly performing some permutations on the data followed by applying any function to that permutations so that bits are uh, shuffled in a sequence so that the patterns cannot be observed. On the other hand, confusion seeks to make the relationship between the statistics of the ciphertext and the value of encryption key as complex as possible. So even if the attacker gets some handle on the statistics of the ciphertext, the way in which the key was used to produce that ciphertext is so complex as to make it difficult to deduce the key. So this can be achieved by the use of some complex substitution algorithm because a simpler substitution such as implemented in the Caesar or other simple algorithms such as mono-alphabetic ciphers, these such simple substitution function would add little confusion. So we will want to add some higher confusion. So diffusion and confusion are very successful methods to make the block ciphers more secure than the other techniques. And these techniques have become the cornerstone of modern block ciphers. So this diagram represents the Feistel encryption and decryption model or structure. So left hand side of the figure shows the encryption structure proposed by Feistel. The input of the encryption algorithms are a plain text. The block of length can be 2 words or any length of bits. The bits must be even so that they can be divided into 2 parts, and this must be a key that is added with the input, one part of the input. The plain text must be divided into 2 halves, the left half and the right half, named as LE0 and RE0. 0 stands for the index of the current round. So the 2 halves of the data pass through n rounds. N stands for number of rounds that an algorithm or Feistel cipher structure takes and processes and combines to produce the ciphertext block. So each round has input left marked as LE and with the number and the right marked as RE with the number, and these inputs are derived from the previous rounds. For example, if you look at the round 2, the inputs are derived from previous rounds such as FE0 is derived from RE0 and RE is derived from with a combination of RE0 embedding with a key and making an exclusive OR with the LE0. So in this case, if we write the equation, we get the left input LE is equal to RE of previous. For example, if we want to uh, find out the left input of first step, we can get the right input of 0 step. Similarly, if we look at the extraction of right input, so we can write the equation R E. For example, we use the term here RE2, that is equal to a combination of RE1 with a key in the previous, and it is OR with input from LE1. So in this case, 16 rounds are used, and each round is based on the same process. However, you can use any number of rounds for such structure. However, all rounds have the same structure. So a substitution is performed on the left half of the data. This is done by the applying the round function f to the right half of the data and taking the exclusive r as we discussed in the previous equation. For after the substitution, there is a permutation is performed that consists of interchanging the two halves of the data. For example, if we used uh, the data LE RE in the exclusive OR gate, next time we're using interchanging the value. For example, RE is simply passed to next step and LE is used in the process. So shaded values are being passed to the next process without modification. So continuing these operations from round 1 to round 16, you produce an output called cipher text. On the other hand, if you want to decrypt the same ciphertext, you provide the input as ciphertext to the decryption algorithm, and the rounds are used in the reverse order to produce the original output, such as plain text. So the actual working of Feistel network depends on the choice of number of criteria and design parameters. The most important are listed here. The number one is block size. So it states that the larger the block size, that means the greater security but reduced encryption decryption speed for a given algorithm. The greater security is achieved by greater diffusion. For example, if you have a large block, you can easily minimize the statistical relevance to block. Typically, a block size of 64-bit has been considered a reasonable trade-off, and it was nearly universal in the cipher block design. However, advanced encryption standards now use a 128-bit block size. The other important parameter is key size. Again, if the key is larger, your algorithm will be more secure. Larger key size means greater security, but again, if you have the larger key size, encryption decryption speed may be lower. So the greater security is achieved by greater resistance to the brute force attack. If you have a large key, there is less chance that the brute force attack will be able to uh, actually decode the information. So again, key sizes of 64-bit or less are now widely considered as inadequate, and again 128-bit has become a common size. Similarly, number of rounds can also affect the performance of Feistel cipher design. The essence of Feistel cipher is that a single round offers inadequate security, but that multiple rounds offer increasing security. So usually you have 16 rounds, but this is not a limitation. You can use any number of rounds in Feistel Cipher design. Another kind of parameter is sub-key generation algorithm. So greater the complexity in this algorithm should lead to the greater difficulty of cryptanalysis. That means your algorithm, the key generation algorithm must be much faster and much better, so it produces a key that is not easily decoded. Therefore, it will enhance the complexity of your algorithm and security of your system overall. Similarly, we used a round function f for adding key to one of the input. If we have the greater complexity, generally means the greater resistance to cryptanalysis. If we have a better function, we have better security against the attacks. There are two other considerations in the design of crystal networks, such as fast software encryption, decryption. So in many cases, encrypting is embedded in applications or utility functions in such a way as to preclude the hardware implementation according to the speed of execution of algorithm becomes a concern. So that means your hardware or software should match each other, therefore to increase the speed of your algorithm. Similarly, ease of analysis is also another concern. Although we would like to make our algorithm as difficult as possible so that no attacker is able to analyze it, there is a great benefit in making the algorithm easy to analyze. That is, if the algorithm is concise and clearly explained, it is easier to analyze that algorithm for cryptanalytic vulnerabilities and therefore develop a higher strength of assurance as to its strength. So as explained earlier, the process of decryption with Feistel cipher is essentially the same as the encryption process, but it is done in the reverse order. The rule is as follows. Use the cipher text as input to the algorithm, but use the subkeys in the reverse order. That is, use any keys. For example, if you use k1 in the first round, k0 in the second round, and so on until the lowest key. For example, if you have the 16 keys, you use the first key in the first round and the 16th key in the 16th round of encryption, and oppositely you use the 16th key in the first round of decryption and uh, first key in the last round of the decryption algorithm. So this is a very nice feature because it means we need not to implement the two different algorithms, one for encryption and one for decryption. You use the same algorithm, but you can reverse the order of keys. So this figure shows an encryption process going down to the left side and the decryption process on the right side for a 16 round algorithm. So for clarity, annotation LE and RE is used for traveling through the encryption algorithm. So in uh, encryption algorithms, we use the term LE and RE. Similarly, for decryption algorithm, we interchange those terms as LD and R, sorry, or D. So means left part of encryption and right part of encryption. Similarly, left part of decryption and the right part of decryption. The diagram indicates that at every round, the intermediate value of the decryption process is equal to the corresponding value of encryption process, with two halves of the value being swapped as discussed earlier. So as you examine a left input and a right input is added. So one input is actually forwarded for the next use, and it is embedded with a key and with using a f function, and it is XOR with left input to produce a value. So our end result is a f function of this input with this key exclusive OR with this input. So this represents the round 15 of your algorithm. So as we have stated earlier that for any round, such as if you're using round 1 in encryption, that will be round 16 in the decryption. Any last uh, any last round in the encryption is the first round in the decryption. So any, for example, if we represented the round 15 here, that will be round 2 of the decryption starting from 16. In simple terms, encryption goes in this way, decryption goes this way. So steps are matched. So similarly, at the decryption round, we get the same input as this one. So that is a f function of a previous step, that is 03A6 embedded with the key 12DE52, and it was XOR with DE7F, and we get the other input that was passed to the future round as 03A6. So similarly, again the same algorithm is used, and we pass the algorithm the same value to the f function, and that is embedded with key, and we pass this value to an XOR gate, which is XOR with the combination of this value. So we get the result f function of one input with the key XOR f function of same input with the key plus another input. So here we have the XOR properties. The XOR property says that if we have three equations marked with XOR, such as A, B, C, such as in this case we have, for example, we have A, that was f function, and we have again A, that was another f function, and then we have B. So this property is equal to the other property. This states that you can write it using A or exclusive or B, exclusive or C. So let me clear a bit. So in this case, if we use this term as A, this term as B, and this term as C, so we replace these values, such as now A is equal to B. This value and this value are equivalent, so we write A XOR A into, let me clear something. and we take this value as C. So our another rule of the exclusive OR states that if you have same inputs such as any two inputs, for example you can use another word D, exclusive OR D, that means both inputs can be 1 or 0, you get the result 0. So if you replace 0 here, you get OR with C, and the C is represented as DE7F. You get the actual output of second value, that will be equal to DE7F. So which is the input of round 15, which will be the output of round 2. So that is the end of this lecture, and in this lecture we discussed some traditional approaches for block ciphers and stream ciphers. We overview a difference between stream cipher and a block cipher. Stream cipher represent a series of bits, and bits can be fed to an encryption algorithm along with a series of bits of a encryption key. On the other hand, block cipher uses a fixed length of bits as an input to an encryption algorithm along with a key. Then we discussed a motivation for a Feistel cipher structure, and we discussed the implementation of a Feistel cipher. If you want to study more, you can read the chapter 4 of the recommended book, and if you ask me using any preferred medium, or you can conduct a question and answer session. Thank you very much.